Let's recap. So in the last video we learnt about the Hadamard gate, and before that we learnt about the NOT gate. So let's draw out the NOT gate. Here it's a box. Diagrammatically it's a box with an X in it, and the matrix associated with that is a 0, 1, 1, 0. And then if we look at the Hadamard gate here, the matrix associated with that is 1 over root 2, 1 over root 2, 1 over root 2, and minus 1 over root 2. And then we also looked at a measurement. So the Hadamard gate takes us into a quantum state, and when we do the measurement, the system collapses back to the classical state. And so this is often represented by an analog meter in a square box. If we plot these on our unitary circle, we end up with, we start here, and we've said that's going to be the 0, and in terms of its vector, it's a 1, 0. So we start here. We apply the Hadamard, we apply the NOT gate, we end up here. So we multiply these two matrices together, and the answer is 0, 1. In reality, of course, the X gate is really the application of a specific frequency, and the frequency being the excited energy state minus the ground energy state over Planck's constant. And when we apply that frequency, the electron jumps from one energy level to the other energy level. But while it's jumping, of course, the magnetic moment changes. And so we say that in our example so far, we said that the ground state represents the spin down position, and the first excited state represents the spin up position. And essentially what we're looking at here or what we're looking at and what we measure in our final system, or measure here, is the spins. So what happens if we put two gates together? So we start from our ground state, we have a NOT gate, we have a Hadamard gate, and let's leave it in the quantum state and not do a measurement for now. So we're going to start here. So that's a 1, 0. Then this is a 0, 1, 1, 0. We've already done that multiplication earlier, and we know we move to this state here. But now if we apply a Hadamard gate to here, you know, in the last example we applied the Hadamard gate to here and we ended up here. This minus 2, minus 1 over root 2 comes into play. So this is our matrix here. Lots of 1 over root 2's, and then in the corner here we have the minus 1 over root 2. And what that does is actually move this vector from here to here, like so. If we do the measurement now, so we add a measurement block here, and this goes off to a classical bit. It's either going to collapse our quantum state here, but it's going to collapse it to one of the two energy levels, or to one of the two spin states that's a classical spin state. So it's again either going to end up here, or it's going to end up here. If we draw on a unitary circle, the complete behavior of the NOT gate, you know, you could call this a state machine, or you could call it its truth table. You know, we know if we start here, we're going to end up here. If we apply a NOT gate to a state of superposition here, it'll stay there. And if you do it's a simple matter of doing the matrix math on the two matrices, and it's the same for this one as well. This one goes back and forth between these two states. So if we apply a NOT gate under here, we'll end up here. Conversely, if we apply a NOT gate here, we'll end up here. and all this is completely reversible, because a quantum computer, or the laws of quantum physics, say it has to be reversible. And then the only other one is this one. So if we are in this state and we apply a NOT gate, we're going to end up here. If we apply another NOT gate, we'll just go back completely reversible. Now if we look at the Hadamard gate on the unit circle, its state machine, or it's this graphical truth table that I've created, we already know from our examples that we're going to go from here to here, state of superposition. And if we are here, we will go to here, and vice versa. Apply another Hadamard gate, we'll go back to where we came from. That's the reversible element. And then the interesting ones that we've already just brushed on is that if we apply a Hadamard gate to this state, we go here, and if we apply the Hadamard gate again, we'll go back. And then the same for these two as well. So if we're in this state, we'll end up in this state. If we're in this state, we'll end up in this state. Just the reapplication of a Hadamard gate. While this seems fairly abstract in terms of what can I do with this, you know, basically I could say I've got a random number generator, because the Hadamard gate gives me a probability of generating a 1 or a 0 50-50 times, depending on the noise and interference in the system. But apart from that, I can't. It's hard to think of a reason why we would have a quantum computer. But when in the videos coming up, we're going to learn a couple of things. We're going to learn that different combinations of gates make up quantum algorithms, and it's the quantum algorithms that allow us to start to solve some of these problems. And right now we're only working on a single bit. You know, when we put two bits together, we really see the exponential power of the quantum computer coming into play. And then we really have to, you know, take this back to, well, what's happening physically? You know, we already know that when we apply a frequency that's equal to excited state minus the ground state over Planck's constant, the spin and the electron will jump to a higher level, to the next quantized state, and the spin will change from a spin down. We assign spin down as a ground state, and it will move orthogonally up to the spin up state. And same for the Hadamard, we apply a frequency for a certain time, and we end up with the electron state being somewhere in between, until we measure it, of course, and then the quantum state collapses and you get back to the classical states. This really, in reality, you know, these frequencies all exist within resonant cavity oscillators, and what we're to facilitate, or to make the quantum calculation happen, really we're going to look at a number of waveforms, because a particle is a wave, and how they constructively and destructively interfere with each other. So having a grasp of where we are on the unitary circle, and later on even on the Bloch sphere, will help us understand how we can perform a quantum algorithm and what that looks like in terms of constructive and destructive interference.